Thank you for the invitation.
Thank you
Hopefully you
for
can
being
see
here.
my screen.
Everything good.
Cool. So we're on the use side of your applications, and I'm delighted by all the technical questions that I couldn't answer about our own technology that I've heard today. So we're more focused on the application, and especially obviously the cost of these and how they're applicable on wind turbines. So a brief explanation why we have wind. A lot of you have backgrounds in physics, but just it's because of the differences in temperatures, right? It's uneven heating of the surface, which generates wind, and then through the use of, in this case, three blades, we can convert some of that wind energy into torque, mechanical torque in this case, and then electrical torque to provide electricity to anyone that needs it. Um, There's something called the boundary layer. So you expect higher wind speeds at the top versus low wind speeds at the bottom. This is important not for this side specifically, but a bit later when I show you kind of the data that we pull out of these sensors. In general, we capture the wind using the plates, which we then convert into mechanical torque. We go through a gearbox, which increases the rotational speed, and it goes into a converter and transformer. From that, we produce electricity. Regarding fiber optic applications, we have one related with sensing, which I'll talk about in detail today, but we have two more. So we have the forge. It's the fiber optic rotating joint, which connects the nacelle, so the static part, with the rotating part, the hub in this case. We have spinning blades, right? And we have communications, we have control, we have a lot of information that goes back and forth to the hub and by the nacelle. It goes through the center of the gearbox, right? So it goes through the whole converter assembly. So imagine like a drivetrain of a car. We have to fit a fiber optics through exactly the center of that, so it goes through the other hole to the hub to get that communication and that information going between the two components. The other fiber optics that we have, it's classic application, right? So communications and data transfer. We use edge computing and edge control at these turbines. So we have distributed nodes across the turbine, and they all communicate with each other using fiber optics. Given the amount of data and speed that we request, it's basically the only option to go. So as an industry, if you're not familiar with it seems like there isn't a lot of technology going. It's a fairly big industrial machine, but it's no longer an option just to point the turbine at the wind and expect that it produces the best technology, right? So I've put here a simple feedback loop here to understand that sensing is a great part why we can have modern turbines. So we can control the turbine actively, not passively like in the past where we had stall control turbines where the blade itself would stall to prevent it from overspinning. Now we control the turbines using the pitch of each blade. We forecast and monitor ambient conditions. So if we can sense something, we can use predictive control to actually control ahead of time. We can monitor energy production. And the most interesting part that people never think about is we can design innovative products and new control features. For example, we have one of our best known features is called rotor lift control. So we basically take the example of a helicopter and flip it sideways. So basically, helicopter would be something like this, and then we put it in a vertical position. So that enables us to basically use the lift that we get from the blades to remove some of the weight of the natural weight, so the gravity component of the nacelle out of the tower. So every time the turbine is in operation, we generate a lift. And that lift means that we have a lower load on the tower, means that we have thinner towers, less material, lower cost. And we do all of this with the aid of sensors and pitching. So we can reduce the bill of materials cost in many, many ways, in the blades, in the towers, in many components, because we have that sensing capability and that actuation capability. Obviously, all of this is controlled by a controller and some smart algorithms. So there's benefits not only for sensing, but also in other aspects of this. I'll I'll focus today on blade load sensing. It's the only one that currently uses fiber optics. And one question might be why, right? So it's located on the blades. So the risk of lightning conduction and lightning is a major issue, and the main reason why we use fiber optics on the blades. We cannot have anything conductive that would basically fry the whole system of the turbine. We also have torque accelerations that use those DCNs, and we have accelerometers, gyroscopes. So it's a distributed system in that case, and we measure a ton of things on the turbine. So each turbine has roughly, I think, close to 1,000 sensors, and all of them produce a lot of data. And we have a fleet of close to 80,000 turbines. So it's a lot of data being generated that we have to monitor and control at the same time. So focusing a bit more on blade loads. Why do we need to measure them, right? So we want to avoid as much as we can that a blade breaks or a tower collapses or we have some form of catastrophic failure. These are machines that are designed to last 20, 30 years, so it's very expensive to get a crane there to get them replaced, right? It's not a sacrificial component, right? They need to last 20 years. Furthermore, it's something that it's cutting edge in the sense that we're producing structures that are very long, very thin, very light because they're spinning, made of fiberglass and other materials. So, or composite materials in this case. So it's for us really important to measure the health and how many cycles they do and the overall performance of said turbine. And if we observe any degradation from what we expect, then we kind of need to stop it and have it inspected or perform some form of repair if needed. So for example, blade bending is one example here. One of the features, you want to extract as much energy as you can from the wind. So that means that the blade would bend more, right? Because we pitch it differently. We want to put the flap angle as close as we can to extract as much energy. That means also that the blade bends. But it's fine. And again, going back to the plot that I had before of the boundary layer, we have also always wind speeds that are higher on the top, usually higher on the top than on the bottom part. But if the blade is bending here, we have an issue because a bending blade will sever its own tower, will cut its own tower. So one of the applications that we use blade loads and kind of some of the other sensors is to, when the turbine blade passes in front of the tower, we pitch out slightly so it extends, it relaxes the blade, and then we're able to pitch back in again. And we do all of these with the aid of sensors, and blade loads is one of the sensors that we use to do this. So there's a lot of, I would say, clever innovations to try to extract as much energy while keeping in mind the mechanical design limitations. So on the right-hand side, I have a plot of blade loads. It's a 3P component, so 3 phases, right? Because we have a 3 bladed system, right? So if one is observing kind of peak bending, it means that the other 2 are not, and they describe a cycle because we're spinning the turbine. And we usually are able to measure strain, flap, and edge, so kind of taking into account that this is a wing, bending moments, we have axial force, twist, and deflection. And we extract all of this information from 2 sensors. They're exactly the same, so in design, but they're positioned in different places inside of the blade. So the sensor is very simple. We have a laser that shines on 2 diodes. Sorry, we have a diode that shines on 2 receivers. And depending on the bending moment locally at the sensor, you can see here on the bottom left that it's glued to the blade. Then we have more light hitting one of the receivers or the other, right? And we can calibrate this. It's a very simple sensor that's covered by an armature to protect it from debris, from there are a lot of things that might happen. Let's imagine the service technicians forgets a tool. Then we have a screwdriver flying around the turbine and the sensor is protected. There's a lot of things that can happen. It was produced internally by Vestas, which was then sold to KK Wind Solutions. And we developed this system many, many years ago. And it's a very simple system. That's why we like it, because it's in our industry, it has to be cheap. It has to be easy to replace if there's an issue. And it has to be on the software side of things, has to be transparent for us, right? So we need to be able to understand if there's an issue with the signal, with the information that's providing. We don't typically accept any black boxes, right? So we need to be reacting really fast if there's a blade issue, because this uh, generates a stop time on the turbine, and that generates millions. And if we're not able to detect this, then as shown by our competition in this sector, we're going to have blade issues, which creates a lot of problems in the long run in terms of reputation and sales and all of the above. So this is our largest turbine. I use the Portuguese stadium because we're Portuguese and where we've designed this. So you get the magnitude of this. It's the size of the stadium with the benches. It's not a stadium. Uh, it's not a football field, right? It's the football field plus all the standings there. So it's the size of a football stadium when it spins. And for scale, this is our moldings for those blades. And you have a person for scale or a couple of those for scale. Basically, where that person, the first one to the right, is placed, it's usually where we place one of the sensors. The other one is perpendicular to that one. So we capture different moments, kind of the flap moment and the edge moment of the blade. So we capture both bending moments, and if we combine them, we have a way to understand with the two axes kind of the movement of the blade. They're gigantic blades, as you might imagine. These are just a few examples, and we have 3 of these in each turbine. More people for scale. This is trying to go roundabout with a blade this size. So that's why we only try to use this offshore as much as we can. And this is a truck for scale, not a person. In this case, it's a truck for scale. So you kind of see the size of this. With size also comes scale, right? Obvious. And it also means that one of these turbines, if it operates for a year, it can power 17,000 households. So one turbine, 17,000 households. Yeah, it's very big, but has a lot of positives on it. So we're installing fields and have 50, 100 of these turbines offshore. So you start to see the scale of renewable energy that we can pump into the grid. Yeah, that's it.
Thank you very
If
much, Gonçalo.
anyone has questions, let me know.
Yeah, so